Okay, so welcome to the next session. This session contains two different topics. So it's two papers on lattice-based work, and then one paper on cryptanalysis. So the first paper is entitled Forward Secure Revocable Secret Handshakes from Lattices. Xian An, Jingpan, Yamin Wen, and Fangu Zhang, and Xiyuan will give the talk.
Okay, hello everyone. Okay, thanks a lot for the introduction from the session chair. And my name is Zhiyuan An, and here I'm honored to introduce our work, Forward Secure Revocable Secret Handshakes from Lattice. A secret handshake is a fundamental privacy-preserving primitive which allows members in the same organization to anonymously authenticate each other and further negotiate a session key. Except for the affiliations, no extra information, including the participants' identities, will be linked. There have been numerous constructions of SH since its proposal. However, none of them considers the issue of key exposure, which is a common threat in SH, since this attack will completely destroy the credibility of the authentication results. One promising countermeasure against key exposure is the so-called forward secure mechanism, where users can themselves update their secret key such that their past transactions can be protected even if a break-in happens. To fill this gap, in this work, we propose the first lattice-based forward secure SH scheme. A secret hand scheme contains a lot of groups managed by the group authorities and the internal group members who can invoke the algorithm handshake to authenticate each other and produce a communication key. To lift this basic model into the forward secure setting, we first divide the lifetime of the system into discrete time periods, and then define a new algorithm update where users can autonomously involve their credentials from the last period into the current one. In particular, the time periods can be viewed as the leaf nodes of a binary tree, where the string of the later proof leaf can be computed from the previous one, where some efficient set operations. It seems that, okay. To fit the forward secure setting, we also stressing the security requirements of SH. And namely now, the forward impersonator resistance demands that even with key exposure attacks, an adversary can still not impersonate a user at a period preceding the one where she was broken into. Besides, we also consider the backward anonymity for unlinkability, which means the user's privacy can be protected before their revocation. Now, we briefly describe how to build a concrete lattice-based instantiation. To establish a new group, GA generates a corresponding group public and secret key pair by use of the lattice trapdoor generation algorithm. And to zero a newcomer into a new group, the newcomer first generates his own public and secret keys, and then sets UPK together with a short proof to GA. With which GA can produce a signature and a time-binding revocation token on this UPK, so that to ensure that user a valid group credential. As for the user secret updates, the US key set is involved by performing basis delegation of latents on the hierarchical time binary tree. Well, the revocation token is scratched from the previous one and the current string in SIS manner. Now we turn to construct the core handshake protocol, where a member A from G1 and a member B from G2 try to authenticate each other. The main gap here is how to use a one-way verify function, the ZK system, to achieve mutual authentication. To this effect, we describe our solution. Note that the verify step of a general ZK system actually checks if the received challenge part is equal to the recovered one. So we mix the original challenge with the lattice-based key exchange element, the KE public key, and we use this new challenge to produce a corresponding response. With a modified proof, the receiver B can first retrieve the whole commitment by recovering the reserved part. And then he can compute the original challenge by simply computing the Hashi function, and finally retrieve the hidden matrix from the mixture. In this way, we can finally get the session key from the underlying KE protocol and generate a MAC tag on this key, and so does A, such that both A and B can authenticate each other in the second flow of the interaction. We stress that this recover with implicit check strategy may be served as a generic approach from ZK systems into anonymous mutual authentication. Now we take a closer look at how this strategy is applied in our scheme. To handshake with B, A conducts the following operations. That is, generate a KEK pair and encrypt her group identity via the GPV encryption, and commit to her revocation token as a LWE function, and fetch a small vector from the current USK set related to the current time string. And finally, embed the KE public matrix into a ZK proof employing the aforementioned technique. Here, to generate such a proof, we will reduce the overall modular linear relations of the operations into an instance of a generic ZK compiler. The security of our scheme is proved in the following theorems based on the SIS and the LWE assumptions. As for the complexity of our scheme, security parameter length related evaluation is as follows. And further, in table 1, we give a detailed comparing of our scheme at the current only known lattice-based one, from which we know that the functionality forward security is achieved with a reasonable increase in the communication cost. Okay, now let's make some conclusions. To settle the problem of key exposure in the field of SH, we first formalize the model of forward secure secret handshake, and then propose a lattice-based instantiation supporting dynamic revocability. In particular, we upgrade the existing static VLR method into an updatable one, that's a revocation token. And moreover, we heuristically show how to, in a generic manner, transform the key systems into anonymous mutual authentication. Looking ahead, there are also still some interesting works for SH, like using structured lattice to yield more efficient schemes, or equip SH with more desirable functionalities, like being fully dynamic or deniable. It's also worthwhile to explore the generic framework or more real-world applications of SH. Okay, that's all for my report. Thanks for your attention.
Thank you very much for the talk. So at the moment, I see no questions in the chat, so maybe I can start asking a question. So did you actually implement also the scheme and get some performance figures or something?
Actually, we have a set the corresponding scheme parameters like the matrix dimension n or the Gaussian's deviation sigma and the matrix norms bound B and get some results. It's GPK size or the credential size or the communication cost. But since we do not use the structured lattice, so the results is not very good. It's up to 10 GB or more. So we haven't listed the results in the paper. It's also future work to improve the performance of the lattice-based SH, since it's till now not really practical.
Yeah, thanks. So what would be the actual lattice dimensions and noise levels if you, for example, would like to have 128-bit security?
You mean how the current security level we achieve?
Yeah. So what would be the number for n if you want to have 128-bit?
If we in our test to achieve a say 100 security bit level, we have to set in around a hours of 2 hours. Let me say it's around 1024. It's approximate.
Okay. Yeah. Okay, so I see no questions in the chat. So then we thank you again for the talk, and we move to the next paper. So
okay, thank you.
Next paper is Leo Dukas, and the title is Estimating the Hidden Overheads in the Btgl Lattice-Based Algorithm.
Talk next to a sleeping baby. So sorry for speaking very softly, but this is the first crypto ASMR talk, so let's go. So I'm going to talk about estimating the cost of lattice-based algorithm and more specifically some hidden overheads. that have been neglected so far. So a very quick overview of lattice sieving. It's a core algorithm in cryptanalysis. It is used to find the shortest vector in a lattice, and it is rarely used directly for cryptanalysis, but more inside strong lattice reduction algorithms such as PKZ. The central task in lattice sieving is, given a large number of vectors, exponentially large number of vectors, is to find all the close-by pair, more specifically all the pairs that are a distance less than 1/2 in terms of in terms of inner products. And the complexity of such a task is naively quadratic, simply comparing all pair, but a lot of techniques have been pushed to take this cost below quadratic, in particular following the work of Lattice-Based. So the naive close pair search proceeds by simply computing all the inner products, and that has a cost n square. But the lattice sieving algorithm from Becker, Duca, Gamma, and Lattice propose to use locality-sensitive filtering, which consists of creating local buckets and only do exhaustive pair search inside those local buckets. So there's many variants of this strategy depending on the shape and the size of those buckets, and this leads to all kinds of time, memory, and success trade-off. These techniques might lead to miss some pairs, but by repeating the technique many times, you hope to catch all the pairs. More specifically, the Btgl algorithm proceeds as follows, at least in its idealized form. We assume that we are given filters that are shaped like spherical caps, and the centers of those filters are efficiently least decodable. And at third, we assume that the centers of those filters are uniform and independent. And you can proceed with a complexity analysis like this, and you obtain the following time and memory complexity. And this is how it is analyzed asymptotically, but also how it has been analyzed concretely. However, in this idealized version, we note that the requirements number 2 and 3 are in tension, because if you want something to be least decodable, it has to be structured. And therefore, the centers won't be perfectly independent. More specifically, Btgl introduced random product codes to solve this issue. And so the set of filters is chosen as a direct product of random spherical codes. So it is a Cartesian product of random things in dimension n over k. So it is kind of a trade-off between something random and something structure. It is random in small dimension, but structure in high dimension. And this allows efficient list decoding. Essentially, the cost of finding the right filters is going to be proportional to the size of the subcodes, and the cost of decoding is going essentially to depend on the number of passing filter plus this overhead. So if the number of passing filter is high enough, the list decoding is efficient. However, this is not random. And the Btgl paper contains a theorem that says that the loss of success probability compared to the ideal case is only sub-exponential when the parameters are well chosen. Though this cost has only been asymptotically estimated so far, and the purpose of this work is specifically to estimate this hidden cost. The way we go about it, the natural way, would try to transform the asymptotic analysis into a concrete one. However, there are techniques used there that are fundamentally lower bounding, and it is very unclear how to do concrete analysis analytically. Another approach could be to simply run the algorithm and see what happens, but it is very infeasible in large dimension, and it is not so clear that extrapolating data from small dimension is very reliable. Instead, in this work, we propose to do focused experiments in large dimension. Instead of experimenting with the whole algorithm, we can do a specific experiment for the random product code. We also propose 2 techniques to accelerate those experiments that are described in the long version of this talk. and we obtain concrete result for a cryptographic relevant dimension. In particular, we obtain a time overhead of about 2 to the 6 in dimension 380, which is about the NIST level 1. You can trade a bit back of this overhead for an overhead on memory, but this is not very advantageous, and this is not does not allow to get rid of the entire trade-off. More specifically, the overhead looks like this. The origin of the plot is the cost as it has been idealized by previous paper, and the curves represent various parameterization of the random product code. And for example, we see here that whatever the parameterization we choose, the cost in the time memory model has 6 more bits than previously estimated. Some quick closing remarks. Should we conclude that there is 6 extra bits of security for NIST level 1? It's not perfectly the case, because those overheads only apply to a subroutine of the algorithm, and it is possible to reparameterize the whole attack to mitigate them a little bit. It also depends on the time on your memory cost model, because if you're allowed to spend a lot of memory, you can get this. And if you consider that memory is essentially free, then the overhead on time is only of 2.5 bits. One frustrating aspect of this world is that it is hard to systematize because it is very experimental and it costs a lot of power to run those experiments. So in particular, this is hardly feasible in an estimator. And it is why an analytic estimate would still be much preferable, but again, it is unclear how to do so. And an open question that I like, because it relates to beautiful spherical codes, is whether we can do anything better than random product codes for instantiating Btgl. Thank you for your attention, and I'd be happy to answer any question.
Okay, so thank you very much for the presentation. So again, I see no direct questions in the chat, so maybe I ask one myself. So this was a specific point with this 2 to the 6 factor. Do you have some intuitive idea how it will vary with the dimension?
So it is sub-exponential, and it is actually quite small in a rather large dimension. So I suspect that it does not increase very fast. Unfortunately, it also gets much more expensive to run bigger experiments. So it might be possible for NIST level 3. I doubt we can run such experiment for NIST level 5. Unless maybe, I mean, all those experiments have been run in Python and NumPy. There is some routine that could be probably made much faster if someone implements them in C++. But yeah, I don't expect them to grow hugely after that.
Yeah. So this factor, do you think it is connected with the fact that it's using a product code? So would it be that using some other code construction could decrease this factor, for example?
Yes, that's the case. Or maybe even we could still use product codes, but something better than random. This can happen. For example, in the lattice world, the best packing are not random, but you can do it slightly better than random. I suspect it is the same for spherical codes.
Yeah.
But the product codes have the random codes have some advantage in terms of implementation, in that it is not clear that all spherical codes would be as fast to decode as well.
Yeah. So a final question from me. So do you know of any attempts to use other code constructions instead of product codes? And
no, I'm not aware. So you need quite some parameterizability of the spherical code. So that's one limiting factor. I know that the original Btgl paper did use product codes, but they tried to improve a bit on the randomness. So they were using random codes and then they were tweaking them a little bit to improve them. But this forces one to store the code instead of streaming it on the fly. So it turns out that this is, again, a trade-off between quality and efficiency. So, but I think it's I really invite anyone with this kind of interest to look at this question.
Yeah, okay. So I see no questions. So I'll thank you again for the presentation, and we will move to the last talk of the session. Okay, so then I will do the introduction, because this is not just any paper, it's the paper receiving the Best Paper Award. So I want to congratulate all of you for this. Yeah, it's online, so there is no award process, but again, congratulations. And yeah, it's breaking category 5 Sphinx Plus with SHA-256, and Ray Palner, John Kelsey, and David Cooper, and Ray is giving the talk.
Thank you. So I guess we've heard about this result a little bit earlier in the conference. So to review, Sphinx Plus is a stateless hash-based signature scheme, which NIST selected for standardization. Here we're going to be presenting a forgery attack that, for some of the parameter sets, in particular those targeting category 5, and that use SHA-256, it reduces the classical security by 40 bits of security. This attack is built on a previous attack or an observation by Antonov, which didn't show how to produce a full forgery of Sphinx Plus, but did contradict the security assumption. The Sphinx Plus team has proposed a tweak which appears to defeat our attack, and it does so by not using SHA-256, where it seems to be vulnerable. So to review the basic design of Sphinx, Sphinx Plus is built on a hypertree where you have something like a Merkle signature scheme that signs the root of another Merkle tree, which so on and so forth, signs a FORS, a few times signature public key. And the focus of our attack is the Winternet's one-time signature Watts Plus, which is used to sign the hypertree roots and the FORS public key. So one detail which is not obvious from the basic description of the design is that the SHA-2 hash function is not used plain, but rather there is a prefix depending on the location in the hypertree, what the hash is for, that's added before a secret or a public key is hashed in a hash chain or a Merkle tree. And the reason for this is because the goal is to have security more like pre-image security than collision security, and there's a lot of places where a multi-target pre-image attack can happen. So there's new things where if you can find a pre-image of some hash, every signature, there's new targets. And so in order to avoid a 1 out of 2 multi-target pre-image attack, the Sphinx designers have added these prefixes so that the attacker has to sort of commit in advance what he's trying to find a pre-image of. Now, this prefix SHA-256 is formalized as a tweakable hash function, and the property it needs to have, according to the security proof, is distinct function multi-target pre-image resistance, or DMSPR. Now, this DMSPR property was shown not to hold at 256 bits of security by Sidney Antonov. And the reason for this is that SHA-256 uses a Merkle-Damgard construction, and so has an internal state size of only 256 bits. So we can find internal collisions and build attacks from there. So in this case, Antonov's attack can be viewed as a modification of the herding attack of Kelsey Kono from, I think, 2004, where we start with a whole bunch of prefixes, and then each time we add a block to produce some sort of a collision so that we are herding the states to fewer and fewer internal states, such that we have a collision of messages starting with all these prefixes. And so they all reach the same internal state. Once we have that internal state, we can add an additional block and find a pre-image in the compression function and use a multi-target pre-image search, because we can then use the structure we built in the herding attack to reach that. And so this was the basis for Antonov's attack. However, this is not quite enough to produce a forgery. And so the reason there is that we have maybe one layer of a pre-image, but there's hash change and stuff, so we need to find further pre-images back to actually create a signature forgery. So this brings us to, how do we extend this to actually produce a forgery? And so the idea here is we want to find a pre-image of some WOTS plus public key, and we want enough control over the private key so that we can sign some digests. We won't be able to sign all of them, but if we can sign enough, then we can brute force search for something we can sign, say the root of a Merkle tree or forest tree, where we know all the private keys used to produce it. And so if that digest can be signed, then we can graft and sign any message whose hash routes it through the WOTS plus signature we forged. Okay, so let's look how we can exploit some structure in the WOTS plus signature. So the WOTS plus signature works as follows. The hash value is written as a base 16 number. A checksum is added to the end, and each digit is signed by revealing a certain stage of a hash chain coming from some part of the secret key. One thing to note is that the thing that gets hashed to produce the Watts plus public key contains these strings PK0, PK1, and that's what's revealed if the digit you're signing happens to be the maximum value, 15 or hex F. And that will be important in producing forgeries. So the idea is the signable digest will take something like the form above, where we have a bunch of X's, which means it could potentially be anything. And then we have a long suffix in the digest consisting only of digits that are hex F. So then we can do this multi-target pre-image search so that we can, so we have a public key pre-image for the Watts plus key, where we don't need to have any control of what's going on in this F region. And so that's where we're going to do all the herding and pre-image search stuff. And we will just treat the part that signs the X's as a prefix, so that for every prefix, we have full private key information, can sign any digit there. So that's all good, except there's also this checksum, and we have to make sure that works out. Now, instead of trying to find a pre-image of the full hash value, we try to find a pre-image of the internal state immediately before the part that signs the checksum. That way we can reuse the checksum from an honest signature. Now, we can, in fact, even increment the value of the checksum, but we can't decrement it. So that means we need the checksum for this message up here to be small enough. Or rather to be, to be large enough, rather. And so that means that these F's are going to make the checksum quite small, so we can get more F's if we choose targets with an unusually small checksum. And then that will impose some additional constraints on these X's. So in particular, the sum of these digits will have a maximum value that can be signed. But as long as the probability is high enough, searching for a Merkle root that can be signed will not be the most expensive part of the attack. So as we see, when we look at the real parameters, we kind of balance the cost between herding, between finding a multi-target pre-image, and between finding a signable digest. And the cost comes out at about 2 to the 217 compression functions, which is about 40 bits of security less than what the scheme is designed for. So, in conclusion, this attack is showing that some of the submitted parameter sets of Sphinx Plus are not as strong as claimed. Now, this is not really a problem with the part of Sphinx Plus that has a security proof, but rather that the tweakable hash function can't be SHA-256 with a prefix, because that does not provide the property. And the problems with Merkle-Damgard hashes when you're looking for more than the collision strength have been well known for, nearly 20 years. So this is a thing to keep an eye on. When you use a hash function like SHA-256, and you think you have more than 128 bits of security, you need to be very careful about that. That said, on the upside, the Sphinx Plus team did provide a tweak, and that seems to address the issues that are uncovered by Antonov's observation in our attack. Moreover, this kind of an attack where you're using the fact that SHA-256 is Merkle-Damgard and doesn't have security always above 128 bits doesn't tend to lead to practical breaks. There are sometimes some length extension bugs that can be a problem, but it looks like everything is with a given prefix is always constant length. So it doesn't look like there should be any length extension bugs. Okay, thank you. I guess anyone has questions?
Okay, thank you very much for the presentation. So at the moment, I see no questions, so maybe I can ask myself. So it seems like the problem comes from the Merkle-Damgard construction for SHA-256. So what would, how would it work if you would instead consider a sponge-based hash function with this DM SPR property?
So the sponge construction as used, a problem may arise if the capacity is not large enough in the sponge construction, but I believe for all the Sphinx parameter sets, the indifferentiability proof should apply up to the claim security level.
Yeah, thanks. Okay, here is a question. Scott Fleurer, would you care to say whether NIST will accept the SHA-2-based Sphinx Plus parameter sets?
So we have not decided formally which parameter sets we are and are not accepting. We, at the very least, do not intend to claim more security than the literature suggests for any parameter set we standardize. And in any event, the performance of things targeting category 5 are significantly worse than targeting category 3. So it would be a shame to standardize something that was only getting category 3 while having performance consistent with category 5.
Yeah, thanks. Okay, I see no further questions. So then I thank you again for the presentation, and thanks to all the speakers of this session. And we'll meet again tomorrow, 7 UTC, 7 sharp. Okay, thanks.